Hello everyone, welcome to the next lecture of the MOS transistors, chapter number 5. This will be the last lecture for the MOS transistor chapter 5. We will cover, it will be a short lecture. We will cover some of the remaining topics, and after that we will jump to chapter number 7, transistor amplifiers, and we'll only cover the sections related to the MOS amplifiers. Okay, so in the last lecture we did some of the examples in which we saw that how we can use the NMOS and the PMOS in different DC circuits. Some of the important remaining topics are the following. Okay, so today we're gonna briefly talk about the substrate, or the role of the substrate. Earlier we discussed in detail in all of the earlier device operations, MOS operations, we connected, if you remember, we connected the body terminal to the source terminal and grounded it. The idea was to make the PN junctions cut off, or to reverse bias the PN junction, right in between the channel and the substrate. So what's the kind of a next step, right? So what will happen when we connect the body to the source and ground it? It will reverse bias the it will reverse bias or cut off the substrate and the induced channel junction. So when we did that in all of our earlier lectures and the discussions, we saw that the body was completely ignored because it does not have any effect on the operation of the MOS transistor. However, in today's lecture, we are going to briefly notice that it is not generally true when we try to make complex circuits and when we have multiple transistors on the same substrate. So what will happen when we have multiple transistors on the same substrates, right? For example, you have a big substrate, you have a bunch of these NMOS transistors, right? So what will happen? And also assume, you can also make an assumption that these transistors are operating at different voltages. Now, in order to make sure that the substrate, the PN junction of the substrate to the channel will remain reverse biased at all times for all the transistors in the cutoff mode, for the NMOS transistor, the substrate needs to be connected to the lowest DC supply available. If we will do that, we will make sure that the channel to substrate junction will be reverse biased. And the same thing is true in a complementary way, in which for a PMOS circuit, we want to connect the substrate to the most positive supply. Right? For an NMOS, the substrate is P-type, so to reverse bias it, we connect it to the negative supply of the circuit. Now, we will see that rather than just connecting the body to the source and grounding it, now if we connect a negative supply to the body, this will start to have an impact on the operation of the MOS transistor. And this is what we are going to discuss. Okay. So this is the voltage that we are applying. This is the voltage in between source and the body. Okay. So consider this NMOS transistor. Initially, for all of our previous discussions, we had a body that was connected to the source. But now we ended up now we will connect the body to the negative supply, or body will be more negative compared to the source, right? So in order for that to happen, let's just assume that it is connected something like this. Okay. Now the body is connected to the negative supply, or it is made negative relative to the source. So what will happen? So what this will do is this will widen the depletion region. Connecting it to the negative supply is going to widen the depletion region, which will result in reducing the depth of the channel. Now, we saw that this means that now we're going to have some positive voltage at the source terminal as well, or the body is at negative with respect to the source. And if that is true, this means that in order to have the same state in terms of conductivity, induction of a channel, and the drain current and all, in order to have the same state of the channel, we need to have a higher value of the VGS, right? So more gate to source voltage is needed to have the same state. So if we connect, so or in other words, if we connect the body terminal to the negative supply, this will directly impact the threshold voltage, right? So we need a higher threshold voltage now. So this means that our gate to source voltage, required gate to source voltage, will be higher to induce a channel as well. Okay, right. So increasing the reverse bias voltage, increase in the VT required to induce a channel. So here's a relationship of the threshold voltage now, right? So threshold. So just a quick reminder: threshold voltage was a voltage that we need to overcome to induce a channel in this enhancement type MOSFET, right? So if we connect, and that was true when the body was connected to the source and grounded. Now when we connect the body terminal and make it negative relative to the source, what we will end up being with, we are going to require more gate to source voltage to induce a channel. So thereby it will kind of end up changing the threshold value. So the required threshold value with the body connected to the negative supply for an NMOS will be represented by this equation, in which VT is the threshold value that we need to overcome to induce a channel. VT naught is assuming body is grounded. And we have a bunch of these parameters that we are going to talk about. Okay. So VT naught is a threshold value when the body was grounded. This phi f is a physical parameter and is approximately equal to 0.6 volts depending on the fabrication processes. And lambda is also another fabrication process parameter, which is shown by this equation, right? So you have this Q is the magnitude of the electron charge, Na is the doping level, doping concentration of the p-type substrate. So with the different values of the doping, or with different doping concentrations, we can impact this gamma value, which in turn will change our threshold value as well. So our threshold value, this gamma in turn threshold value also depends on the permittivity of the silicon and the oxide capacitance too, right? So we have a bunch of these parameters that are impacting the threshold value that is needed, or our gate to source voltage needs to cross this threshold value to induce a channel, right? So determination of the threshold value is also important. And this is where the body effect also comes in, right? Or the biasing of the body terminal also comes in. If it is related to the ground, if it is connected to the ground, then we don't need to worry about that extra potential that is applied. However, if it is connected to in an NMOS, if it is connected to if the body is connected or the substrate is connected to the made negative or the negative supply compared to the source, relative to the source, then our threshold value will increase. Right, so we see that from the previous equation. For any changes in this biasing of the substrate value will result in changing the threshold value, right? So if we increase the VSB, the threshold value will increase. And what was our overdrive voltage? Our overdrive voltage was this, right? So this means that for a same VGS, if we have a same VGS applied to the gate terminal, and if our VT will increase, our overdrive voltage will decrease. And if our overdrive voltage will decrease, our drain current is directly proportional to the overdrive voltage, right? To the square root of the overdrive. So our drain, so decreasing this thing is also going to decrease the drain current. So what essentially is happening is, if we want to keep everything the same, the channel parameters the same, the drain current the same, then we have to increase the gate to source value if we have a body terminal connected to the negative supply, right? However, if we have the same gate to source voltage value and we ended up connecting the substrate to the negative terminal, this will end up decreasing the drain current. Okay, right, so this is what we talked about. Important thing, another thing that you may have realized from here is, for a same value of the VGS, right? Over here we have a same value of the VGS. Increasing the VSB will decrease the overdrive voltage and decrease the current. So if you have realized by now is we can also change the value of the drain current based on the source to body bias value. So our body terminal, our this body or the substrate or the body terminal can also act as a gate. We can also change this value, this potential at the body terminal to control the amount of the current that is flowing through the channel, right? So this phenomenon is known as the body effect, right? So we can control, by changing the body voltage, we can control the value of the drain current. So this is known as the, this phenomenon is known as the body effect, and this, by this lambda parameter over here, this, yeah, this gamma parameter over here is known as a body effect parameter. Okay, now we are going to very quickly talk about a few other very quick concepts. So temperature, we are going to see the effect of the temperature on the MOS operation. Both VT, threshold value, and the K dash are temperature sensitive, right? And we know that our drain current is directly proportional to the K dash, and it is also directly proportional to the threshold value. Essentially, it is proportional to the VOV or VGS, which is VOV minus VT, VOV plus VT. Okay. So what will happen is, if we will, and if you remember from the PN junction lectures earlier, that the magnitude of the threshold voltage decreases by approximately 2 millivolts for every 1 degree Celsius rise in temperature. So as the temperature will increase, the threshold value will decrease. And if the threshold value will decrease, the current will also decrease. Oh no, so sorry. So the decreasing the threshold value will increase the overdrive voltage and the current will increase. Right? So if by increasing the temperature, if the threshold value is decreasing, this means that if we have a same gate to source voltage, the effective voltage beyond the threshold voltage will be more now. This will increase the depth of the channel, conductivity of the channel, and in turn the drain current. So we see the effect of the temperature on the threshold value and the operation of the device. Now let's see that, right, so let's see what will happen with the K dash, the process transconductance parameter, which was mu n Cox for an NMOS. So what will happen to the K dash? The K dash will also decrease with temperature. So as temperature increases, the K dash will decrease. Now, as we know that the drain current is directly proportional to the K dash, so if the K dash is decreasing, the drain current is also decreasing, right? So if we look at it holistically, we have two parameters that are being impacted by the temperature. One is the threshold voltage and one is the K dash. Increasing the temperature is ended up resulting in increasing the drain current. Increasing the temperature ended up decreasing the drain current. However, in terms of the impact or the change in the drain current, the K dash factor is a more dominant one. So overall, our drain current will end up being reduced. So overall, when the temperature will increase, the drain current will decrease. Although our drain current is increasing due to the threshold result, decreasing threshold value and increasing temperature, but the K dash parameter is a more dominant one. Okay. Another important concept is about the breakdown and the breakdown voltages. Okay, so if we keep on increasing the voltages at the drain terminal, right, so there will come a time at which the substrate or the junction between the drain and the substrate junction will suffer an avalanche breakdown, right? If we are constantly increasing the voltage at the drain terminal, the junction that is made over here, right? So this is the drain and this is the substrate. So this junction. So this junction will suffer an avalanche breakdown, right? And this occurs at 20 to 150 20 to 150 volts. And um, if you remember the some of the details from the PN junction chapter or the diodes chapter, earlier part of the diodes chapter, when we discuss the PN junction, that an avalanche we are going to have a rapid increase in the flow of the current. So this avalanche is known as a weak avalanche. Another important thing related to avalanche and higher voltages is a phenomenon known as a punch through. This phenomenon also occurs at higher voltages, comparatively higher voltages, if we keep on increasing the drain voltage, but we keep the drain voltage not significantly higher, but around at 20 volts. A phenomenon will happen known as a punch through. So the punch through phenomenon is more dominant in shorter channels. So the phenomenon is that when the drain voltage is constantly increasing and will reach to a certain point, let's say 20 volts, the depletion region that is surrounding the drain region will extend through the channel to the source terminal. And then the current will increase very rapidly, right? So this will not permanently damage the device, right? And of course, this will be more dominant in the shorter channels. However, if we will continue to increase the voltage beyond this 20 volts, right? No, actually, we saw that for the drain voltages, if we even for this range of 20 to 150 volts, we are going to have an avalanche breakdown. The current will increase, but this is still a weak avalanche. Then at 20 volts, we saw the effect of the punch through. However, it's important where that high voltage is applied. For example, if you are applying a high voltage, which is approximately 30 volts, to the gate terminal in between the gate and the source, this will result in the permanent damage to the device, because what is going to happen is this will break down the oxide layer, right? So this will result in a permanent breakdown of the device. So it's important to understand the effect of the breakdown or the operational voltages of the MOS transistor. Okay, so there is one more quick thing we're going to talk about is the velocity saturation. So there is kind of this saturation or the highest mobility or the drift velocity of these charge carriers that we can have. For example, in silicon, it is approximately 10 to the 7 centimeter per second. And the idea is that as we are increasing the voltages, the drift velocity is increasing. Right. If you remember, in one of the very starting lectures, we ended up showing this equation of drift velocity to be directly proportional to the voltage values and inversely proportional to the length. So as we are increasing the voltage values, the drift velocity will increase for the charge carriers. However, it will reach to a saturation level, even for less than 1 volts, right? And this is true for most of the modern devices where our channel lengths are very smaller. So for our short channel length devices, the charge carriers will reach to a saturation velocity for less than 1 volt. So increasing the voltage is not going to help in terms of the increasing the drift velocity and or eventually increasing the drain current. Okay. So important thing is that once that velocity saturation will happen, the drain current will no longer be related to VGS by the squared law relationship, right? We saw that for a specific drain to source voltage when the transistor is operating in the saturation region, right? When we apply a VDS, sorry, this is gate to source, VGS and ID. So this is a squared law relationship of the drain to current and the gate to source value. However, if our voltages will reach 1 volt or even at lower than 1 volt at saturation levels, it will no longer remain this a squared law relationship. However, we will realize that this will more become linearly related to the gate to source voltage, because the transconductance parameter or the transconductance GM, and if you remember, GM was KVOV, right? It will become constant. So your V of V will become, so your K value, which was Kn dash W over L, or it was mu and Cox W over L, right? So all of these parameters will become constant. And so what will happen is the ID, the drain current, will become linearly dependent on VGS, and the square law relationship will not hold beyond a certain voltage at which the velocity saturation will occur. Okay, so now we have one final topic before we end this chapter, and that is talking about this depletion type MOSFET. All the MOSFETs for the last many lectures we have been talking about are the enhancement type MOSFET. The enhancement type MOSFET is right, so consider an example of an NMOS, right? So first we do is we apply a gate to source voltage that needs to exceed a threshold voltage to induce a channel. Once the channel is induced, and we apply more gate to source voltage or a higher overdrive voltage that is increasing the conductivity of the channel more and more, or in the depth of the channel, right? So this is the enhancement type MOSFET. And of course, when we have a VDS applied as well, then the current will start to flow, the drain current. And depending on the VDS value, whether it is less than the overdrive voltage or equal or greater than, it will be operating either in the triode region or the saturation region. So what exactly is so that was the enhancement type MOSFET, in which we are inducing a channel first, and then we are increasing the conductivity, enhancing the conductivity. So that is why that was called as an enhancement type MOSFET. Now we're going to talk about a depletion type MOSFET. In a depletion type MOSFET, we do not induce a channel. The channel is physically implanted there. Assume that the channel is already there, right? And if the channel is already there in a MOSFET, then irrespective of that, we don't need a VGS to kind of for the drain current to flow, right? Because we initially apply the VGS. VGS still has a role, but we initially apply the VGS till a level of a threshold voltage to induce a channel first for its operation, right? So now if the channel is already there, then all I need to do is to apply that drain to source voltage, and the current is going to flow. So the most important distinction is, and we're going to discuss more detail. So the most important distinction is that in a depletion type MOSFET, a channel is already physically implanted, right? So for a depletion type MOSFET, we still have the same thing: N-type source, N-type drain, and a P-type substrate. Now, so important thing is that even at a zero gate to source value, right, even when we don't apply any voltage to the gate to source terminal, or we just ground it, and we apply a drain to source terminal or a drain to source voltage, a current will start to flow, right? So this is exactly an opposite to the enhancement type MOSFET. In enhancement type MOSFET, we needed to induce a channel for its operation, otherwise it will not operate. For a depletion type, the channel is already there, so we just apply the VDS and the drain current will flow. Right, okay. However, now, so what will happen when we apply a gate to source voltage to a depletion type MOSFET? So in a depletion type MOSFET, channel is already there, sure. So if we apply a gate to source voltage to the channel, so this means that there is no threshold voltage, or the threshold voltage in a depletion type MOSFET has a different meaning. Now, if we apply some voltage to the gate to source rather than zero, this is going to behave as an overdrive voltage, right? So it is going to deeper the channel, it is going to get more electrons from the majority charge carriers from the source and the drain to the channel. It is going to increase the conductivity of the channel. So the phenomenon, all the phenomena are the same. Applying a gate to source voltage to a depletion type MOSFET is going to increase its conductivity. So in that specific, so we will realize that we are operating the depletion type MOSFET. Also, we can operate that in an enhancement mode by applying a gate to source voltage. Right, so the depth of the channel and its conductivity can be controlled by gate to source voltage, and exactly the same manner as enhancement type MOSFET. Okay, right. So another important concept is again coming back to this depletion term here. So in our depletion type MOSFET, what we have discussed by now is we have a MOSFET with the channel already there. So we don't need a gate to source voltage. We will just apply a VDS and the current will start to flow. However, if we will increase the gate to source voltage more, the conductivity of the channel is going to improve or is going to increase, and the more drain current will flow. So what will happen if you will apply a negative VGS? So if you will apply a negative VGS, that will start to repel the electrons, right? So if I will go back to this was right. So this was our NMOS, right? And just assume that this channel was already there with all of these electrons, right? So if we apply, if we will increase this VGS value, it is going to attract more and more electrons here, right? So the conductivity is increasing. However, if I will start to apply a negative VGS here, right? So these electrons will start to move away, or the conductivity will start to reduce. So it is going to have this opposite effect. So applying a negative VGS will causes the electrons to be repelled from the channel, right? It was an N channel. So the channel depth will reduce and the conductivity will decrease. So a time will come. So as we are applying this negative VGS to the gate terminal in a depletion type MOSFET, a time will come when the channel will be completely depleted of all the electrons, right? And this is why it is called as a depletion mode, because what we are doing is we are kind of depleting the channel of its charge carriers. Okay, so this is what we just talked about. So let's assume that you have, so let's start again. So we have a depletion type MOSFET where the channel N channel is already there. We apply a VDS and a current will start to flow. Then what we did is we applied a gate to source voltage. Its conductivity starts to increase and our current will start to increase. Now we reverse the polarity of the VGS and starts to decrease its voltage values. So we have a negative voltage at the gate terminal. When there is a negative voltage at the gate terminal, it will start to repel all the electrons in the channel. So the conductivity will start to decrease and the current will start to decrease. A time will come when the channel is completely depleted of all the electrons and the current will become zero. Okay, so that voltage, by the way, is known as a threshold voltage for this depletion type MOSFET. Okay, so this is what we just said. So the negative value of the VGS at which the drain current will become zero is the threshold voltage of the N channel depletion type MOSFET, right? So the MOSFET, so the important thing is that the MOSFET, depletion type MOSFET, can be operated both in enhancement mode by increasing the value of the VGS from 0 or by applying a positive VGS, and in the depletion mode by applying a negative VGS. Here is a symbol of the depletion type MOSFET. If you look closely, it looks exactly the same as the enhancement type MOSFET, except this wider, darker region, right? So this is this region suggests that or indicates that a channel is already there. A channel is physically implanted. So that is why it's a depletion type MOSFET. Okay, right? As the existing channel. So the channel is already there. So this is the depletion type MOSFET. Okay, so let's look at the IV characteristics here. Right, so this is ID, this is VGS. So this means that we have a, so so even when the VGS is 0, we see that for a positive drain to source voltage, we have a current that is already flowing through the channel, right? Even when the VGS is 0. Now, as we increase the value of the VGS, the drain current will increase. The conductivity of the channel will increase, the drain current will increase, enhancement mode operation. As we decrease the value of VGS, the electrons will be repelled, the conductivity will decrease, the depth of the channel will decrease, and the drain current will decrease. So the drain current will continue to decrease. A time will come when the drain current will be equal to 0. That is known as a threshold voltage, and this mode of operation is known as a depletion mode. And this is what we just talked about. For a positive VGS, it will attract more electrons. The conductivity of the channel will increase, and when we apply a negative VGS, the electrons will be repelled, the channel becomes shallower, and the conductivity will decrease. Yeah, and as we are increasing the VGS in the negative direction, a time will come when it will be when the channel will be completely depleted of the carriers of the electrons, and the drain current will become equal to 0. Okay. So with that, this is it. This is a depletion type MOSFET. So this is the end of the chapter number 5 on MOSFET. In the next lecture, we're going to start the next chapter, We will talk more about how we can use these MOS amplifiers, how we can use these MOS transistors in the amplifier circuits, how we can design the amplifier circuits, different configurations of the amplifier circuits. We're also going to talk about how we can develop these linear amplifiers. Okay, so with that, thank you so much, and have a good day. Bye bye.